This video will look at an important example of a continuous random variable called the normal distribution. It's also sometimes called a bell curve because it sort of looks like a bell. So this is a population model. And since this is a population model, just a reminder, when we're talking about averages, we use the symbol mu. And when we're talking about standard deviations for a population, we use the symbol sigma. So it looks something like this. The center of my curve is mu, and the spread is sigma. The notation for the normal distribution is n has a center of mu and a standard deviation of sigma. So this notation will tell you n for the normal distribution. Mu, this is the middle of your curve. And sigma, this is your standard deviation. So just practicing notation a little bit, going back to this example that was in an earlier video, labeling all the values in the following paragraph. The average weight of all cats is 54 pounds with a standard deviation of 10 pounds. So when I'm talking about the distribution of all cats, that has an average of 54 and a standard deviation for all cats of 10 pounds. In contrast, when I'm talking about a sample, like a sample of 2 cats that have an average weight of 13 pounds and a standard deviation of 2 pounds, the average for a sample is the symbol x bar. And the standard deviation for a sample, that's the symbol s. So we're going to look at things more like this. And if I knew that the weight of all cats followed a normal distribution, it would look something like this. I would put that 54 in the center, and I would count up and down by that standard deviation. So I would add 10 to get 64. I would add 10 again to get 74. In the opposite direction, I would subtract 10. Subtracting 10 would make this 44. Subtracting 10 again would make this 34. So I can get a feel for sort of the likelihood of weights if I'm looking at all big cats. 54 is fairly likely. It's somewhat unlikely that I would get something like 80. I've drawn the distribution here. Calculate the z-score for a cat that weighs 70 pounds and determine if it'd be unusual. Well, I can already see in my picture here that 70 pounds would be within 2 standard deviations. It would show up about here. And since it's within 2 standard deviations, it would be considered usual. But I'm still going to find the z-score because that also tells me about the rarity of the event. I find z-scores by taking the value, subtracting the center, and dividing by the standard deviation. In this case, I've got my value of 70 minus my center of 54, and I'm counting by 10 or so. When I type this into a calculator, I get a z-score of 1.60 or so. For the lesson today, I'm going to be rounding all of my z-scores to the nearest 10th hundredth place, 2 decimals out. We'll see why when we're using a table of normal values, but essentially this gives me enough coordinates to create some sort of a grid. And we said that this would be considered usual. And the reason why it's considered usual is because it is within 2 standard deviations of the center. In general, there are really specific percentages of values that show up within 1, 2, or 3 standard deviations away. That rule is called the 68, 95, 99.7 rule. And it tells me the following. 68% of the data with under a normal curve is within 1 standard deviation of the center. So drawing the picture out, if I start at the center and I go 1 and 2 tick marks down, I should have about 68% of my data in that area. Now, just to note, if you're trying to visualize this, one standard deviation is hitting halfway on the downswing on both sides. So that's how I visualize what that one standard deviation mark looks like. 2 standard deviations away from the center, I have 95% of the data. I would consider this to be usual. Something is usual if it happens 95% of the time. By extension, we might say something is rare if it happens less than 5% of the time. (99.7%), so 68 is within 1 standard deviation, 95 is within 2, 99.7% of the data is within 3 standard deviations of the center. So let's use this approximating formula, this empirical rule, to estimate some areas together. Recall that the weight of all cats normally distributed with an average of 54. And I'm counting by tens. 1, 2, 3 tick marks. This thing goes on forever in both directions. But even 3 tick marks is a really, really long distance away. 2 standard deviations is pretty unusual. More than 3 is very, very rare. How likely is it to have a weight between 34 and 74? Well, looking at my graph, 34 shows up here. That's 1, 2 standard deviations down. And 74 shows up here. That's 1, 2 standard deviations up. So 34 to 74, this is within 2 standard deviations of the center. Matching that with the rule above, this is 95% of the data. So I should have about 95% sitting there between 34 and 74. Let's say I was looking at the next one, 24 to 84. 24 is 1, 2, 3 tick marks down. 84 here is 1, 2, 3 tick marks up. So if I'm looking at the area within 3 standard deviations, that's 99.7% of my data set. So within 3 standard deviations of the center, I'm getting an area of about 99.7%. Suppose on a recent exam, scores are normally distributed with an average of 76 and a standard deviation of 4 points. If someone said, I graded the test on a curve, this might be what they mean by that. So I'm going to draw the picture out. So I have my bell curve there. Notation-wise, my average is 76, and I'm going to count by 4s. So 76 shows up here. And I'm going to count by 4s in both directions. This is 80, 1 tick mark above. This is 72, 1 tick mark down. The first part of this asks me for the probability between 72 and 80. And I feel like I luck out there because this is 1 standard deviation down, and this is 1 standard deviation up. I'm within 1 standard deviation. And if I'm within 1 standard deviation, that's approximately 68% of the area. If you're watching this video along at home, I'm going to ask that you pause this and try to figure out this next piece. 68% in the center, how much do you think that leaves for this tail right here, where I'm looking at 80 or higher? Pause the video and try to find the area of 80 or higher. Let's take a look. So the entire curve is 100%. So if I have the entire curve is 100% and I have 68% so far, this tells me that the size of these two tails that I have dotted here must be the remaining 32%, the complement of 68. But I only want one tail. I want from 80 and above. So to find this area for one tail, I'm going to take this 32% and I'm going to divide that by 2. This gives me a probability of 16% or so. So even in situations where it's not between or within 1, 2, or 3 standard deviations, if it's a question more like what's the likelihood that it's less than some value or more than some value, I still might be able to answer that question, but I'll have to get creative with the way that my pictures look. Let's try another. Again, if you're doing this thing at home, pause the video, do both examples 3 and 4 here. I want you to find the area between 10 and 40 if the average is 25 and the standard deviation is 5. If the average is -3 and the standard deviation is 7, I want you to find the area between -17 and 11. Pause, try it out. Let's take a look. So for this first one, my center is 25. Halfway on the downswinger or so is 1 standard deviation away. I'm counting by 5s. So 25, 30, 35, and way the heck up there in the boons, I got 40. Opposite direction, I have 25, 20, 15, and really, really low, I've got 10. Between 10 and 40, this is 1, 2, 3 standard deviations up. This is 1, 2, 3 standard deviations down. If I am within 3 standard deviations of the center, this is telling me I have approximately 99.7% of the area by the 68, 95, 99.7 rule. This one, same idea. I just have to be careful because I have a negative as my average there. So I'm going to watch my signs as I add and subtract things. -3 is the center. I am adding 7 to this. I'm down $3 and I gain 7. I'm at 4. 4 plus 7 gives me 11. I'm matching up with one of those values. That's a good start. Other direction, -3 take away 7, puts me at -10. -10 take away 7 more, I've got -17. I'm looking between these values on both of them. Between -17 and 11, this appears to be 1 2 tick marks up and 1 2 tick marks down. If I'm within 2 standard deviations of the center, then matching that up with the rule from earlier, 68, 95, 99.7, that's the 95 part of the rule. So a follow-up question, what if I wanted to know the likelihood of 10 or less? So not -10, but +10. And on my graph, I see something a little bit weird. -3, 4, and 11. 10 is right here, and it's more than 1 standard deviation, but it's less than 2 standard deviations. And I want that amount or less. So I have a little bit of an issue. This does not line up with that 1, 2, or 3 standard deviation away trick. So let's figure out exactly how many tick marks away it is. Let's calculate the z-score. And the z-score does a really nice job of giving us sort of a relative standing. Again, we find the z-score by taking the value we care about, subtracting the center, and then dividing by the standard deviation. For example, I can see this is more than 1, almost 2. So if I had to guess, maybe 1.8 or 1.9 something. My z-score is going to be the value I care about. I care about 10 in this problem, minus the center of the curve, so minus -3, that's my average. And I'm counting by my standard deviation of 7. Minus a negative is the same thing as addition, so this looks like I have 10 plus 3 or 13. 13 over 7 gives me something like approximately 1.86 or so. Now, unfortunately, the 68, 95, 99.7 rule doesn't line up when I have decimal numbers of standard deviations like 1.86. When I'm in these kinds of situations, I use a table. Here's going to be my general process for dealing with problems for any future normal distribution sort of setup for finding areas. I'm going to draw a picture to make sure I can visually see what I'm trying to find before trying to do any complicated math. And the math won't be too bad. I'm finding z-scores and I'll have a process for looking them up. So when I'm drawing the picture, I put the average in the center, -3. I'm counting by 7, so here I had 4 and 11. Here I had -10 and -17. The value that I care about is 10. That's 1.8, not quite 2 standard deviations away. And I wanted that amount or less, so I'm shaded to the left. My next step is going to be to calculate the z-score. I take my value minus the center over the standard deviation. And I got something like 1.86 when I did that. Finally, I need a process for looking up the z-scores. In the D2L page, there's a file called normal table, and it looks something like this. Let's explore it together. This thing has 2 sides to it. I have a negative side, has negative z-scores going along there, and I have a positive side. And both sides, I want you to notice the blue part, or the shaded in part, if you're colorblind. This is shaded to the left. Let's look at the other side. Also shaded to the left. So just kind of as a general observation, the normal table will always give the area to the left. So whatever value we're finding inside of the table, this will be the same as whatever that z-score is or less. So in this problem, it's shaded to the left of a z-score of 1.86. So I need a way to look that up here to find that area. Now, I'm noticing this is a positive number, so I'm going to go to the positive part of this table. And I'm noticing that this forms a grid. Now, this is how this is working. This right here is giving me the first 2 digits of my z-score, and the columns up at the top, that's giving me the last digit of my z-score. So when I see something like 1.86, this is saying go to the 1.8 row of the table and see where that meets the 6th column. 1.8 row meets the 6th column right here at a table value of 96.86%. Since my picture is shaded to the left and my table is shaded to the left, this is the area. The likelihood of having a value of 10 or less, now it doesn't matter if there's an equal sign underneath this or not, it will be the same answer, is approximately 96.86%. Again, a takeaway for this page is whenever the thing is shaded to the left, your answer will be that number from inside of the table. So a follow-up question might be, great, but what if it's shaded to the right? How am I going to find the area if it's shaded to the right? Or what if it's between two values? So let's look at everything that could possibly happen on this next page. Suppose that the number of, and I'm going to go between these two documents here, number of hours of sleep a person in the US gets is normally distributed with an average of 8 hours and a standard deviation of 0.5 hours. I'm going to draw my graph. Draw my picture. I'm going to find my z-score, and then I'm going to look it up. Middle of my curve is 8. I'm counting by 0.5, so this is 8.5, 7.5, 8.5 plus 0.5, this is 9, this is 7, this is 9.5, this is 6.5. The value I care about for this particular problem is 9.25, and that happens right here. And this is one of the ones that I can almost visualize. Do you see how this is 1, 2, about 2.5 standard deviations away? When I calculate the z-score, I'm anticipating that it's going to be really close to 2.5. Let's figure out which way we're supposed to shade. I'm looking at numbers less than 9.25. Well, all of these numbers on this side are less than 9.25. So I'm going to have this picture shaded to the left. If it's shaded to the left, that's good for me, because that tells me that whatever value is inside of the table, that's going to be the area that I'm looking for. So let's find the z-score. I'm going to take my value. My value in this case is a number that I care about, this 9.25. I'm going to subtract the center of my curve, and I'm going to divide this by the thing I was counting by, the standard deviation. So in my calculator, I'm doing value 9.25, and I should do parentheses, be careful about that. 9.25 minus the 8, the center, divided by 0.5, that's standard deviation. This gives me 2.5, which I can see it's 2.5 tick marks away. A reminder, I'm always doing this thing to at least 2 decimal places because I need to be able to look this thing up on this grid. So when I'm trying to look it up, I'm going to find the 2.5 row, and I'm going to find where that meets the 0 column. Let's give it a go. I'm on the positive side. I'm trying to stay positive, super corny. And I'm finding where the 2.5 meets the 0. And the 2.5 meets the 0 right here at the 0.9938. So my table value is 0.9938. The reason why I draw my picture is I'm trying to see if this is a reasonable estimate for the area or not. This looks like almost 100% of the curve, so I'm feeling pretty good about this. The likelihood of having 9.25 hours of sleep or less, that's almost everyone. To get more than 9.25 hours, you're sleeping like a king there. That's the top point, whatever, 0.6% or so. Really unlikely to get more than this amount of sleep. 99.38% of people are getting 9.25 hours of sleep or less. Let's try to figure out how many people are getting more than 7 hours of sleep. So I'm going to go through the same process here. I'm going to draw my picture. Center of the curve is 8. I'm counting by 0.5, so this is 7.5 and 7. Oh, I've already found my value. Great. This is 8.5, and this is 9. I'm looking at 7 and values bigger than 7. Well, all of these numbers are bigger than 7. This is shaded to the right. I'm going to find my z-score. I can see what it should be, though. It's 2 tick marks down, so I should be getting -2. If you can just see what it is intuitively, go with it. If you can't, go through this formula. The formula takes the value, I subtract the center, and I'm dividing the standard deviation. Value is 7, the center is 8, and I continue to count by 0.5. Typing this in a calculator. And I end up getting, sure, -2 as it looks, standard deviations away. I'm writing that as -2.00 because I need to make sure that I have 2 digits after the decimal, so that way I can have both the row and the column for the value I'm trying to find. So let's try it out. I'm on the negative side. I go to -2.0, where this meets the 0, and I get a table value of 0.0228 or so. Now here's what this means. On my picture, I have in this left tail .0228 shaded from this z-score and down. But I don't want this little area. I want this much larger area going in the opposite direction. I want the area going to the right. In order to find the area to the right, I just need to take the complement of the area to the left. Right and left are opposites. So whenever I'm trying to find some region that's shaded to the right, my answer is going to be 1 minus the value from the table. In this case, I have 1 minus 0.0228, which gives me a probability of 0.9772 as the likelihood of someone getting 7 or more hours of sleep. So 97% of people get more than 7 hours of sleep. This is kind of the standard for minimum numbers of hours of sleep you should probably be getting. Let's look at the likelihood of getting between 7 and 9.25 hours. I'm going to draw my picture. This has 2 numbers. All these other examples only had 1. So when I find z-scores here, I'm actually going to have 2 z-scores. I'm going to have a z-score for the larger number. I usually use L for large. And I'll have a z-score for the smaller number. I tend to use S for smaller. So center is 8. I'm counting by 0.5. And I'm shaded between 7, that looks like it's 2 standard deviations down, and 9.25, that looks like that's 2.5 standard deviations up. I'm going to calculate the z-scores. The z-score for the large value, the large is 9.25, minus the center of 8, divided by the standard deviation of 0.5, and I get 2.50. The small z-score, I have my value is 7, minus my center is 8, my standard deviation is 0.5. When I type that into a calculator, I get negative 2.00, and I'm having a lot of deja vu going on here because these z-scores of 2.5 and negative 2 are exactly these values that I had from before. So let me cheat a little bit and let's just write down what my two table values are. So my table value for this first number here, my large table value, is 99.38. My small table value, when I looked up this z-score, was 0.0228. Now, for this particular problem, I want the area between these numbers. Well, let me show you what these things represent on my picture. This large z-score is everything from this large value over to the left. This includes the entire area that I want, but unfortunately, it also includes this tail that I do not want shaded in. So I am overcounting by the amount that I have in this value to the left. That amount is this 0.0228. So 99.38 is too big, and it's exactly too big by 0.0228. So if I wanted to fix this and find the area in the center, if I take the large table value and I subtract this area of the smaller tail that I don't want, this should give me the area in the middle. So the probability of having between 7 and 9.25 hours of sleep, I'm going to take the large table value, and I'm going to subtract from this the smaller one. When I do this, I end up getting, for this particular problem, 0.9710 or so. This is a skill that you should continue to practice. Much like learning a new language, you have to continue to practice this until you gain mastery over it. But I hope you're getting a feel for how this table is working. And I wanted you to see at least a core example of each of these things. If it's shaded to the left, you're using the table value. If it's shaded to the right, you're using 1 minus the table value. And if it's between two numbers, subtract those two table values. Let's look at another one. So this is a graph that I got after playing a video game called Pikmin 3. When I finished the video game, it gave me this graph. It said, you finished this in 31 days. Days in the video game, not in real life. I didn't spend 31 days playing this thing. And it also showed me what was going on with the average number of days for other players. The number of days or less, so any number of days less than 31 would be a score that's better than mine. Any number of days that was bigger than 31 represents a score that's worse than mine. So I saw that I was better than average, but my follow-up question here was, how much better am I compared to everyone else? Am I in like the top 5%? Am I in the top 30%? What is my overall standard? So let's check it out. It says estimate the average and the standard deviation for this graph. This might be a little bit hard to do on the overhead, but let's do our best. And it also asks for the standard deviation. Now my average is going to happen right at the middle of the mound. So trying to visualize this on this graph, it looks like it's between 40 and 50. So I would anticipate an average of about 45 days. My standard deviation is the distance that it takes to get halfway on the downswing. About halfway on the downswing, I would say, is about here. Notice that this has gone from 45 to 55. That is approximately 10 days away for that standard deviation. So zooming out now that I have these two pieces, and you might run into this in the real world too, where you see some data that has a normal distribution, but they don't provide you with all of the average and standard deviation. You can always recover that data though. So I've estimated the average, it's the middle of my curve. I found the standard deviation that was halfway on the downswing, which was at what's called the inflection point. That's halfway where it meets from a curve going down to a curve going up. And I'm going to rewrite this on the distribution below. Normally distributed, first number will be 45, and I'm going to count by 10. So 45, 55, 65. Other direction, I have 35 and 25. Now, I'm wondering how many people did better than me or how good I am in general compared to other individuals. My score was a 31, and 31 is shown somewhere up about here. And I want that much or less. If you're following along at home, go ahead and pause the video and see if you can figure out the z-score for this value now that I have the picture. And see if you can find the probability using that normal table. Assuming you paused it and gave it a go, let's try it out together. I'm going to take the value that I care about, 31. I'm going to subtract the center, 45. And I'm going to divide by the number that I'm counting by. My standard deviation is 10. When I type this into my calculator, I get negative 1.40. This is in the negative 1.4 row, and this is in the 0 column. I'm going to look this up inside of my table. I'm in the negative 1.4 row. I'm in the 0 column. This meets right here at that value. My table number is 0.0808 or so. My picture is shaded to the left, so this tells me the percentage of people that got a better score than me was 8% or so. So to phrase this another way, Mr. Wary was in the top 8% of scores. So I'm finding sort of the percentile, my relative score compared to everyone else. Now, in some of these situations, you might actually want to go in reverse. So instead of knowing, say, the top 8% of scores, which is still usual, it's within 2 standard deviations. So this is hardly something to brag about. I might be curious, what does the top 1% of scores look like, or the top 5%? So let's see if we can answer some of those questions. Okay, suppose that it takes 45 days. Zooming out, let's look at this together. Suppose that the number of days it takes to collect all the fruits in the game are normally distributed with a center of 45 and a standard deviation of 10. What does the 90th percentile look like? So let me show you what's going on. Center of the curve is 45, and I'm counting by 10. I want the 90th percent mark. So what's meant by this is they want the total area to the left. And I don't know exactly where this is going to end. This is a complete guess. So I might have a really bad picture here. I hope you'll forgive me if it ends up being a pretty bad picture. But there'll be some unknown score that I'm trying to find. So in context of the problem, the 90th percentile is actually the lowest 10% of scores, because more days meant worse scores. So this would actually represent sort of some of the worst players of the game. That's okay. Let's try to figure out exactly what that cutoff would be. Now, what I've been doing so far, and I'm just going to have that general process up here on the top of my page here, is I have been starting out with some x value that I know, and from that x value, I've been finding the z-score by doing that value minus my center divided by my standard deviation, and then I've been looking this thing up in a table. And when I've been looking this thing up in my z-score table, I've been finding whatever that z-score starts out with, that row and the column, and I've been taking the spot where they meet. So I start with an x value, and I end the problem with a percentage that I'm finding inside of this normal table. This is kind of the opposite of that. I don't know what this number is, but I do know the percentage. This is 90%, or 0.90. So I'm going to do this process in reverse. I'm going to find 90% inside of the table. After I find 90% inside of the table, I'm going to plug it in the z-score formula. And finally, I'm going to solve for my x value. So I'm doing the same steps in reverse when I start out with a percentage. So let's start with 90% inside of the table. I'm trying to find the z-score for that amount, because I don't know how many tick marks away I am. So I'm looking inside. So 0.90, as close as I can on this part of the grid. And I'm noticing on the negative side, I'm just not seeing that. So I'll go to the positive side. And I'm getting close here at 0.8944. I can probably do better. 0.8997, that's almost 90%. That's pretty dang good. 0.9015. I think we have a winner here at 89.97. Let's see what this z-score is. So the closest I can get inside of the table was 89.97. 89.997 is sitting in the 1.2 row, and it's sitting in the 8 column. So this is the z-score of 1.28 for 90%. So plug it into the z-score formula. Okay, so instead of z equals, I actually have the number. I have 1.28 is equal to the value that I'm trying to solve for, minus the center of my curve, 45, divided by the thing I'm counting by, in this case, 10. And finally, I'm going to go through the process of solving for my x value. When I'm solving, I do opposite. So to get rid of this division, I'm going to multiply this 10 over. To get rid of this subtraction, I'm going to add this 45 to the other side. I'm writing this 45 at the front here, and I'm doing this mostly so I can see exactly what this z-score of 1.28 is telling me. A positive z-score of 1.28 says from the center, you are going to go up 1.28 standard deviations. I'm going to type this into a calculator and see what I get. When I did this, I got 57.8 as the number of days for the 90th percentile. I'm going to do one more of these things with you. I'm going to calculate the best 25%. This is the 25th percentile. So I'm going to draw my curve. And I'm starting out with the area. I know the area in this tail is 25%, but I don't know what my x value is. So what I'm going to do inside of my table, I'm going to get as close as I possibly can to 25% to see what my z-score should be. So in my table, I'm looking for 0.25. Seeing it kind of close on the bottom here. 24.2, that's close. 24.5, 24.8, 25.1. It looks like it's between these two. When you're finding that it's between two values, you can always average out these z-scores. So this is a z-score of negative 0.67. This is a z-score of negative 0.68. So between the two, negative 0.675 or so. I would really take any value between negative 0.67 and negative 0.68. It shouldn't matter that much in your overall result. Now that I have the z-score, I'm going to put it into the z-score formula. So this tells me that z is equal to my value minus the center divided by the standard deviation. As a final step, I'll solve for my x value. I'm going to do this all in one step this time. I'm going to multiply this 10 over, and I'm going to add the 45. So from the center, 45, I go down negative 0.675 standard deviations. I'll type this into a calculator. And when I do so, I get a value of 38.25 days for the lowest 25% on the curve, which represents the best 25% of scores. If you're feeling pretty good about this and you want to get a tiny bit more practice in, suppose that IQ scores are normally distributed with an average of 100 and a standard deviation of 15. What score would correspond with the highest 5%? That's the same thing as the 95th percentile. Try to give that thing a go and see what you come up with. This is a really nice problem to practice that's still on the same level of difficulty of the things that we've just tried. We will see this normal distribution show up again and again for the rest of 243. It's one of these foundational curves. Things that follow a normal distribution. Temperature follows a normal distribution. Height follows a normal distribution. If you're looking at IQ scores or most exams, they also tend to follow this normal curve. It shows up quite a bit.